Welcome to Efiwe, excellence without stress.
Hi guys, it's me again, your favorite physics tutor. In our journey into excelling without stress, into becoming a great physicist, into becoming a great scientist, we're going to take another topic today, which is the gravitational field. And this is our table of contents. You're going to learn about the law of universal gravitation, the gravitational potential, escape velocity, potential energy, the gravitational field. Just as other topic has always been, is also going to be a very interesting topic, and you're going to understand everything you need to know about the topic. So, introduction. The gravitational field is a region or space around a mass in which the gravitational force of the mass can be felt. This is actually very simple. You notice that anytime you jump up or anytime you throw something up, thing actually comes down. No matter how much how fat or how big the thing is, there is a particular pull that will always draw such thing down to the ground. But if you throw a paper, you might be saying, but when I throw a nylon or something, it doesn't come down very fast. The reason for that is not because the gravitation is not affecting it. It's because of air resistance. The air resistance of such body is actually what makes it to stay in the air longer, not the fact that gravitation is not affecting it. Look at the picture close to this place. You can see an apple falling. You remember the story of Isaac Newton, where we said Isaac Newton was sitting under a tree and he wondered that why is it that fruit falls, that why is it that the fruit does not stay or remain on the tree? Then he thought that there must actually be a particular force that is making such fruit to fall on the ground, and that was how he discovered the force of gravity, which is the gravitational force, and that is what we're going to look at today. So the gravitational field is a region or space around a mass in which the gravitational force of the mass can be felt. That is that space around you. Yes, we cannot see the gravitational pull, but it's actually affecting us. It's just like magnetic force also. When you take a metallic material close to a magnet, the force will actually pull that magnetic material towards the magnet, and that's just the same thing with the gravitational force. So the law of universal gravitation. Don't forget what I told you about law. I said when something is a law, it is generally accepted everywhere. So what is the law of universal gravitation? Newton's law of universal gravitation states that every particle in the universe attracts every other particle with a force that is proportional, that is directly proportional to the product of their masses and inversely proportional to the square of the distance between them. So just look at this picture. We have two masses. We have M and we have a smaller m. So how can we know the force of attraction between this body? The force of attraction is actually this first m, this bigger m, and this small m, the multiplication of that is the product, then divided by the square of the distance between them. There is a distance. This m is here, the other m is here. So the Newton's law of universal gravitation is telling us that for us to know the force of attraction between these two bodies that are separated by a particular distance, what you just need to do is multiply the product of their masses and then divide it by the square of the distance apart. Don't worry, we are going to go to our board and I'm going to just explain that. So let's quickly go to our board. So from our definition, we said that Newton's law is what? Newton's law of universal gravitation states that the force of attraction is what? F, which is the force of attraction, is directly proportional to the product of the masses. We had a big M and we had a small m. It's directly proportional to the product of the masses. That's another small m. And inversely, so proportional to the what? That is 1 over what? Their distance apart, which is the square of their distance apart. So if we bring these two together and we change the proportionality sign into an equals to, we're going to have F is equals to, and don't forget, I told you that anytime we're changing a proportionality sign to equals to, we're going to introduce a constant. So for this topic, our constant is going to be the capital G. So multiply by the capital M. We can call it M1, M2, it doesn't matter. And the small m, then divided by the what? R square. And this is the formula for the Newton's law of universal gravitation. So if you want to know the force of attraction between two bodies, this is the formula you're going to use. The gravitational constant multiplied by the mass of the first body, the mass of the second body, and their distance apart, and that gives us the formula for the force of attraction. And that's what we have here. You see, we said F is the force of gravity, G is a gravitational constant. And you know what a constant is? It doesn't change every day. So which is 6.67 times 10 raised to power minus 11. We have m, which is mass of one object, and m is equal to the mass of the other object. R is the distance between the two objects. So there's no particular order of writing the m. When you are multiplying two numbers together, it's not compulsory to write the smaller or the bigger one first. Any one can be written because it's multiplication. So let's go to the next slide. So gravitational field intensity. So gravitational field intensity at a point is the force per unit mass of an object placed at that point. From this definition, we can get the formula of what gravitational field intensity says. That what gravitational field intensity at a point is the force per unit mass. It's just trying to tell you that when you say gravitational field intensity, how intense the gravitational pull is on that body at that point. So gravitational field intensity at a point is the force per unit mass of an object placed at that point. So G, which is the gravitational field intensity, is equal to force divided by the what mass. And I'm sure you can get the unit. You know, our force is measured in Newton, our mass is measured in kg. So that is just going to be our Newton per kg. As simple as that. So let's go to the next topic. The relationship between G and G. The smaller g is acceleration due to gravity, and the bigger g is the gravitational constant. So what's the relationship? What's the relationship between these two? You know, this g, which is acceleration due to gravity, and this capital G, which is the force of the gravitational constant. Is there a particular relationship between them? We're going to derive it. So if the force of attraction F between two particles of matter separated by a distance is given by this, so we have that F is equal to G, capital G mm, and over r squared. You know how we derived this formula from our Newton's law of universal gravitation, and you know that also F is equals to mg. We talked about that during our class on measurement. So let's go back to our board and let's try to derive this. So let's get the combination between the two. So let's clear the board. So we said that from our Newton's law of universal gravitation, we have that F, right, is equals to what? G, which is a constant, right? Then m, m over what? Over the r square. So also we have another F also, which is equal to mass times acceleration, which we are going to call as what? Mg. So let's equate these two together. So mg is equals to what? G, right? m over what? R square. So let's take our G. So G is going to be equals to G, capital M, the small m, over what? M, then the R square. So this m, we cancel this m. So the G is equals to what? G, 1m, over what? R square. So this is the relationship between the G and the what? And the capital G. So that's what relates the two of them together. Very easy. I'm sure you understand what we just explained, and that's why we have this. So G, which is the acceleration due to gravity, can also be the big G, which is the gravitational constant, multiplied by the mass divided by what? Distance apart, which is r squared, or you call it the radius of the earth. So that's the relationship between the two. Gravitational potential. The gravitational potential at a point is the work done in taking a unit mass from infinity to that point. So the work done from taking a body from infinity to that point is what is called the gravitational potential. Gravitational potential at a point is the work done in taking a unit mass. A unit is just a part, one mass, from infinity to that point, and the unit is given by this. So U is equals to G multiplied by m. If you have one m, no problem. If you have two masses too, no problem. So you can either say the gravitational potential U is equals to G m over r, or G mm over r. It depends. If you have two bodies, you multiply the two bodies together. If you have one body, you use just one body. So the gravitational potential decreases as r increases. Are we clear with that? The gravitational potential U is just, even you can even depict it from the formula. U is here is as if we're saying U is inversely proportional to r. That is what this formula is actually trying to say. U is inversely proportional to r. That's why I said the gravitational potential decreases as r increases and becomes 0. And becomes r. Okay, they said the gravitational potential decreases as r increases and becomes 0 when r is infinitely large. The negative sign indicates that the potential at infinity 0 is higher than the potential close to the mass. So from this formula, we have that our U is the gravitational potential energy, G is the universal gravitational constant, M is the mass of the Earth, M is the mass of the body, and R is the distance of the body from the center of the Earth. So that's our gravitational potential. So now the next topic is escape velocity, just as the name implies, escape velocity. So this is the minimum velocity required for an object to just escape or leave the gravitational influence or field of an astronomical body. What this is just trying to say is just a particular velocity an object can have such that the gravitational pull will no longer affect it. So this is the minimum velocity required for an object, e.g. satellite, rocket, to just escape or leave the gravitational influence or field of an astronomical body, e.g. Earth, permanently. So that is what the escape velocity is. So can you see it now? So this is the escape velocity. This is this rocket or this rocket escaping the pull of the gravitational influence. So we have this, that we have that our W equals to gmmr. This energy is given in the form of Ke is equals to half mv squared. So you remember that kinetic energy, which is the energy a body possessed by virtue of its motion, is half mv squared, is also equals to what? Gmm over r. You remember when we told you that gravitational potential is Gmm over r. So we're going to equate these two together and we're going to derive our escape velocity. So let's do that. Let's go to our board and derive this. And don't forget also that our G is Gm over r squared. Those things are very important and we're going to put it into our equation. So recall that Ke is equals to what? Half mv square. You have that your is equals to Gm over r. So putting these two together, we have half mv square is equals to Gm over r. So you know we're trying to get the escape velocity, and don't forget that your G, your small g, is also equals to what? Gm over what? R square. So you have also that your G is equals to Gm over what? R square. So we can get our V equating these two together. Let me clear the, okay, no, don't let me clear the board. So we have that mv square over 2 is equals to what? Gm over what? R. So if you cross multiply, you know that mv square r is equals to what? 2, right? Gm. So let's take our v square. So v square is equals to what? 2 Gm over what? M what? R, right? You know, M is here, M is here, so we have cancelled the M. So V square is equals to 2G over R. So V is equals to 2, square root, let me delete that, Control Z, Control Z. So V, Control Z, Z, okay. So V is equals to the square root of 2G over R. So putting the relationship between these two in the equation, look at, we have that our G is equals to Gm over R squared. So we're going to have to change this Gm over R to, God, sorry, excuse me. So look at it now. We've gotten our V square, which is 2Gm over R. So changing this, which is the square, and putting it in this equation is going to be the square root of 2Gm over R. Recall that your G is equals to Gm over R square. Let me start again. Potential energy is, kinetic energy is half mv square, and remember that gravitational potential also is Gmm over R. So putting these two together, you're going to have V square from here is equals to 2Gm that is 2 multiplied by this gmm over r. One m is going to cancel the other m. So your v, which is the escape velocity, is the square root of 2gm over r. So recall, when we were trying to state the relationship between acceleration due to gravity and gravitational constant, we had that g is equals to gmm over r square. So gm is also equals to what? Gr square. So putting this gm is equals to gr square into this formula that we got here, we're going to have escape velocity is equals to 2g r square over r. So 1r we cancel 1r. So what is going to be left? We're going to have that our escape velocity is equal to the square root of what? 2g and r. I hope we are very, very clear with that. So let's go to the next slide. Energy in gravitational field. So a satellite moving in an orbit around the Earth has both kinetic and potential energy. We know what kinetic and potential energy is. Kinetic energy is the energy a body possesses by virtue of motion, while potential is the energy a body possesses by virtue of its what? Of its position. So the centripetal force, this is the formula for the centripetal force, is equals to mv square over r square, and it's also equals to gmm over r square. You remember this gmm over r square. This is the gravitational attraction F. This is the formula for the gravitational force. So F is equals to gmm over r square. So just as we've been doing, we've been equating and equating. Also for kinetic energy, we have that half mv square is equals to gmm over r. This is just trying to put the relationship between the kinetic energy and the potential energy. And don't forget, the total energy in the orbit is potential energy plus kinetic energy, which is gmm over r, which we have here, plus the minus gmm over r. The following conclusions can be drawn from the equation. The magnitude of the total energy is equal to that of the kinetic energy of the satellite. The kinetic energy of a satellite in an orbit increases as the radius of the orbit decreases. So we can see that. So look at r is here. So kinetic energy will decrease as what? R is increasing. It's just as simple as that, because the r is actually in the denominator. PE here will be, if P is increasing, R will be decreasing. Same thing goes for the KE. If KE is increasing, the R also will be increasing. The kinetic energy of a satellite in an orbit increases as the speed of the satellite increases, while the potential energy of satellite in an orbit is twice its kinetic energy and of opposite sign. Please, these conclusions are very, very important. So quickly, we're going to go into the differences between mass and weight. So what mass and weight? Mass is the amount of matter contained in a physical body, while weight is the gravitational force with which a physical body is attracted toward the center of the earth. What we just need to understand is mass is constant everywhere, while weight changes. Why does weight change? Because of the acceleration due to gravity. That's why weight changes. That's why the weight of a body changes. So don't forget the unit of mass is kilogram, while the unit of weight is Newton, and so on and so forth. So go through these differences, and because you can actually come across so many questions on it. So questions, let's solve some questions. So the first question says that state Newton's law of universal gravitation and give the mathematical relation. So let's go to our board and just quickly use that as our summary for this class. So you recall that we said Newton's law of universal gravitation states that it's just that force is what? Directly proportional to m1 and what? m2. And also that same force is inversely proportional to the what? Square of the distance apart. So the mathematical relation we're asked to get is just F is equals to, we know that changing proportionality sign to equals to, we need to put a gravitational constant or a constant. So we have the m1, m2 over what? R square. So, and that is the mathematical representation of that Newton's law of universal gravitation. So the next question says, calculate the gravitational potential U. Don't forget, this is the formula at a point on the Earth's surface. So we were given the mass. So the mass was So we're given the mass. The mass was 6.0 times 10 raised to the power 24. The radius was 6.4 times 10 raised to the power 6. And the we know that our gravitational constant is 6.7 times 10 raised by 11. So let's go to our formula. We're asked to find the gravitational potential. So Control delete. So our gravitational potential U is equals to Gm over what? R. And so we're giving, you know that we're giving our G is a constant, which is equals to 6.67 times 10 raised to power minus 11. We're giving our radius. So what was our radius? Let's check our radius. Our radius was 6.4 times 10 raised to power 6. Our radius was 6.4. So our R was 6.4 times 10 raised to power 6. What else were we giving? Our mass. What was our mass? Our mass was 6 times 10 raised to power 24. So 6 times 10 raised to power 24. So putting all this together, we're going to get our gravitational potential. So our U will be equals to 6.67 times 10 raised to power minus 11 times, okay, let me write it down. So we're going to have it to be equals to 6.67 times 10 raised to power minus 7 minus 11 times our M, 6 times 10 raised to power 24, then divided by our R, which is 6.4 times 10 raised to power 6. So what's going to be our answer? Our answer, let's go to our calculator, and we're going to have it as our answer is 6.25 times 10 raised to power 7. Okay, let me write that here. 6.25 times 10 raised to power 7, and that is our gravitational potential. As simple as that. So let's go to the next question. Okay, the next question says calculate the escape velocity of a satellite from the Earth's gravitational field. So we have our G, which is a constant 9.8, and our R is still the same thing. So don't forget that your VE, which is escape velocity, let's delete this, Control delete. So recall that your VE, which is the escape velocity, is just the square root of what? 2G multiplied by the R, right? So that was going to be the square root of 2 times 9.8 times 6 times 10 raised to power 6. So if you use, let's use our calculator to do that. So we have square root of 2 multiplied by 9.8 multiplied by 6 multiplied by 6 times 10 raised to power of 6. Then okay, so what's that going to give us? So that's equals to 1.1 times 10 raised to power that's equals to 1.1 times 10 raised to power 4, or 10844. So that's what we're going to get, and that's our escape velocity. And so you have an assignment to solve. Please try to do the assignment on your own. It's very easy, and it's very easy to solve. I'm sure we've explained everything you need to know and everything you need to understand. If there is any issue, you can as well reach out to us anytime, but I'm sure that we've basically covered everything you need to know. Thank you, and see you in the next class.